Welcome back. After topic 1 and 2, you're expected to know 1. How to make enclosure. 2. How to count the total number of radiation surface in. 3. How to identify black or gray surface. 4. How to find view factor value. Then you're ready for topic 3, radiation heat equations and solution steps. A. Understand the net radiation heat rate. First, the net radiation heat rate is defined as all radiation heat leaving the surface minus all radiation heat coming on the surface. Therefore, if the net radiation heat rate has a positive sign, it indicates more radiation heat leaving the surface. Otherwise, more is coming. Second, there are two kinds of a net radiation heat rate. The one is Qij, which is net radiation heat rate exchanged between surface I and surface J. The other is Qi, which is net radiation heat rate from a single surface I. Third, we will use this three-surface enclosure as an example to explain these two net radiation heat rates. A. As illustrated in this example, the circles represent the solid surfaces at a different temperature T1, T2, and T3. The numbers represent the radiation heat rate. The arrows represent the radiation heat flow direction. B. Based on the definition of net radiation heat rate, Q12 represents all radiation heat leaving surface 1 into 2 minus all radiation heat coming on surface 1 from surface 2. Similarly, Q21 represents all radiation heat leaving surface 2 into surface 1 minus all radiation heat coming on surface 2 from surface 1. By checking these two net radiation heat rates have the same magnitude but opposite direction. C. Let I equal 1, which is we focus on surface 1. According to the definition of net radiation heat rate, Q1 represents all radiation heat out minus all radiation heat in. It is also represent that net radiation heat exchange from surface 1 is due to net radiation exchange with surface 2 and with surface 3. B. Solution steps and radiation heat equations. The big picture for radiation roadmap here is, through the steps, we will determine what kind of an enclosure it is for our problem. Then, based on the enclosure category, we select the proper radiation heat equation for unknowns. Next, we will use two examples to show you how to do it. See example 13-3 for black surface enclosure. A cylinder of 3 black body surfaces, A1, A2, and a side surface A3. Open at bottom except for area A1. This is empty open area. is placed at a large room at this temperature, we need to find net radiation heat value Q13 and Q1. Here is the data. Radius R1, R2, the distance of L between two disks, area A1, A2, A3, and the temperature T1, T2, T3. That's what we know and we need to find out. Step 1. Identify all the heat transfer modes. Their radiation heat flows from surface A1 to A3, from surface A1 to A2, and from surface A2 to A3. Step 2. Make enclosure. Since our system is open at the bottom, we make enclosure by adding the surface A4 and assume the surface temperature is 300 Kelvin and emissivity of 1 to represent the large room. Now the system is closed. Step 3. Decide enclosure geometry on whether it is 2D or 3D. By comparison, surface area A1 is much less than A2, A3, and A4. Its contribution to the radiation heat exchange can be neglected. However, since we're seeking Q13 and Q1, the radiation heat rate from surface A1 has to be remained. Therefore, the enclosure geometry is three-dimensional. Next, we count the total number of radiation surface for our enclosure. There are 4 surfaces, A1, A2, A3, A4, and each has its own temperature. Therefore, the total number of radiation surface for this enclosure is 4. Step 4. Check enclosure surface on whether it is gray or black. We have 4 surfaces which are all black because each has the emissivity of 1. From step 1 to 4, we draw the conclusion it is a 4 black surface enclosure. Step 5. Based on the enclosure category, we go to radiation roadmap in a minute, then select the proper radiation heat equation for Q13 in equation 1 and Q1 in equation 2 by checking. In order to get Q13 and Q1 value, we need to find the view factors first. Step 5.1. Calculate view factors. A. We start with surface 1 because it is plane. Then the view factor F11 is 0. B. We go to surface 4 because surface 1 and 4 are on the same plane. Then view factor F14 is 0. It indicates there's no heat flow from surface A1 to A4. C. We apply summation rule. Since n equals 4 and let I equal 1, J changes from 1 to 3 to 4. Then we plug equation 3 and 4 into equation 5 to get equation 6D. For view factor F12, we go to table 13.2 because it is 4 coaxial parallel discs of A1 and A2. Then we select the view factor equation, plug into numbers to get view factor F12 value. E. We go to equation 6, plug into F12 to get view factor F13. Step 5.2, plug into numbers. In equation 1, this is A1, F13, sigma, temperature to the 4th power to get Q13. In equation 2, this is Q12, this is Q13, which is calculated from equation 1. This is a Q14, which is a 0. Plug into numbers to get Q1 value. Now we go to radiation roadmap. It includes solution steps, enclosure categories, and radiation heat equations. There are 5 enclosure categories. 1, 2, 3, 4, 5. For our case, it is 4 black surface enclosure. Therefore, these 2 equations were selected for Q1 and Q13, where 4 is replaced by 3. The rest of the equation will be discussed later. D. Example 13-4, 3 gray surface enclosure with re-radiating surface. A metal liquid at this temperature is poured into a cylindrical container. The container is well insulated from large surroundings at this temperature. The container has diameter D and distance from the surface of a metal liquid to the top of the container. The surface of metal liquid has this temperature and this emissivity. We need to find the net rate of radiation heat transfer from metal liquid surface to the surroundings. That's what we know and what we need to find out. Step 1, identify all the heat transfer mode. There's radiation heat flow from metal liquid surface to the surroundings surface. 2, make enclosure. Since the system is open at the top, we make enclosure by adding surface A2 to represent the surroundings surface, and assume the temperature is 300 Kelvin and emissivity is 1. Now the system is closed. Step 3, decide the enclosure geometry on whether it is 2D or 3D. By comparison, A1, A2, A3 are close to each other. Therefore, the geometry is 3-dimensional. Next, we count the total number of radiation surfaces for this enclosure. There are 3 surfaces, A1, A2, A3, and each has its own temperature, T1, T2, T3. Therefore, the total number of radiation surface for this enclosure is 3. Step 4. Check enclosure surfaces on whether they're gray or black. We have one gray surface A1, one black body surface A2, and one is unknown for surface A3. From step 1 to 4, we draw the conclusion it is a 3 gray surface enclosure. Step 5, based on enclosure category, we can go to radiation roadmap to select the proper heat equation for unknown Q1, 2. Before we do that, let's introduce the concept of re-radiating surface. As shown in this illustration, the re-radiation surface represents an insulated surface on one side. As a result, there is no heat flow in or out. On the other side, it absorbs all radiation heat and then radiates all back. It acts like a mirror. Now, look at our 3 surface enclosure. On one side, it is well insulated, therefore there's no net heat flow in or out. On the other side, there's radiation heat flow coming on the surface A3 due to the temperature difference. In order to match zero net heat flow, the same amount of radius heat is reflected away from surface A3 due to the temperature difference. Therefore, surface A3 acts as a mirror, and it is a re-radiating surface. Therefore, now our enclosure becomes 3 gray surface enclosure with a re-radiating surface. Next, we go to re-radiating roadmap, check the enclosure categories. For our case, this is our closure category. This is the equation we select. For the rest of the work, based upon the equation select, you find out the view factor, then plug into numbers. For the radiation heat rate, it leaves to students' practice. At this point, we covered topic 3 with 2 concepts and 2 skills discussed. Have fun. See you next time.